welcome back. This is lecture 38. So up until now, if you recall from lecture 1 to lecture 37, we have spent considerable amount of time and covered considerable amount of ground, covering various aspects of RFIC design. We have talked about what are the metrics of importance in RFICs. For example, how do you calculate noise, how do you evaluate noise, sensitivity, distortion, and several other metrics. We talked in fair amount of detail how a receiver architecture looks like. We spent considerable amount of time optimizing some blocks, for example, LNA, different types of mixers. We talked about passives, how to go about designing passives, what are the things that we need to take care, what are the things that you need to do in order to ensure that the on-chip passives are less lossy. Then we moved on to transmission lines. We spent considerable amount of time talking about transmission lines. Transmission lines are one of the important aspects in an RF design that makes it different from an analog circuit design. And we tried to bridge the gap between an analog circuit mindset and an RFIC mindset from a designer's point of view, while being respectful of the fact that everything is ultimately circuit design, right? So the underlying principles still hold, but we need to understand the pitfalls of what we should be more aware of while designing an RFIC, especially when you are coming from an analog circuit background. We spent then some considerable amount of time also in optimizing an LNA in the presence of long transmission lines, right? And we also saw in under what conditions you need to bother about the transmission line effects and in under what condition you do not have to bother about transmission line effects. After spending almost 2/3 of the course on the receiver side and talking about the matrix of importance, then we switched to the transmitter side, and then we again talked about the up conversion mixers on the transmitter side. We talked about image rejections for receiver and an IQ mixer in case of a transmitter side. Then we moved on to power amplifiers, right? We spent a few lectures, albeit not in that amount of detail, but we spent a few lectures on different types of power amplifiers and the matrix of importance in power amplifiers. And I hope that you will be able to appreciate what are the things to take care or at least look for while designing power amplifiers. As you might have noticed till now, what we have not done is we have not spent any time on designing local oscillators, right? We have not spent any time designing LO. This is done on purpose. One of the reasons I chose not to spend so much time on LO is because one of the reasons is there is a dedicated NPTEL course on phase lock loops, which deals with LO design, local oscillator design in a much broader sense. But having said that, I would be amiss if I do not spend at least some amount of time in motivating as to what are the things, how do you go about thinking about designing a local oscillator, right? So at the fag end of this course, right, so almost the last lecture, let's put our heads together and see how to think about going about designing a local oscillator clock, right? Okay, what is the heart of a local oscillator clock? What do we want? We ultimately want a sinusoidal input in time domain which has a single desirable frequency at whichever band I am targeting to operate at, right? So in a local oscillator, in an LO, so we want firstly clean clocks. When I say clean clocks, I mean frequencies which do not drift with time and can be set accurately, right? Note that I am not too bothered about the amplitude. Why? Because ultimately, if you have seen, all the mixers operate in a 1-0 mode, right? In the sense that they are either on or off, right? As long as I can make sure when they are turning on and off, I am good, right? Because ultimately, even if I have some sort of sinusoid, I can always put a bunch of inverters and make the edges sharp and make it a square wave clock, right? So the frequency is important and the phase is important by extension, right? Okay. Next thing we want the LO to be electronically programmable. Correct? Why electronically programmable? Because you have so many bands in which you want your receiver and your transmitter to work on. And how do you select a band? You basically move your LO, right? You, depending on the band of interest, you choose your local oscillator frequency. Now, you do not want to make a receiver in most cases where your frequency is fixed, because you will be probably taking your cell phone and moving to different time zones and you'll probably be using different carrier frequencies depending upon whatever features you have subscribed for, right? Which essentially means that each of these might be operating at different frequency bands, which means you would like to have electronically programmable LO. Otherwise, you need a oscillator for each of these bands, which is not a very efficient solution, right? So on top of these, you require multiple other things. You would like to have very low noise, right? That is a very important part of a clock, right? But unfortunately, we will not be able to cover noise in any amount of detail in this course. Okay. What I'll try to do is to cover is to at least give you a framework to understand how to generate clocks on chip and how to use those on chip clocks to generate other subsequent clocks, right? So let's get to that. When we say that we have to design a clock, what do I essentially mean? Basically, I need to have a framework to generate a sinusoidal signal. Now, what is the easiest thing that you can think of that can generate a sinusoidal output? It's a local LC oscillator, right? If you have an LC oscillator, which is perfect, that is no loss, no resistance associated with any of these components, and you have, let's say you start this LC oscillator with some initial voltage Vc naught across this capacitor, then as the time progresses, you are going to see a sinusoidal waveform which will start from Vc naught, and it will have a frequency of 1 over 2 pi under root LC. Correct? So far so good. But if this were a solution, then there shouldn't be separate courses on the PLLs, and there should not, a local oscillator should be pretty easy to generate. Obviously, the problem is this is not ideal, and one of the reasons of non-ideality is the fact that there is a parasitic resistance associated with an inductor or a capacitor, and that we have already seen multiple times. And if this is the case, what will happen? Now, depending upon this value of this resistance, I mean, if you have a resistance, this nice sinusoidal waveform will eventually die off. The rate at which it will die off will depend on the value of the resistance. Larger the resistance, quicker it will die off. But the key thing to note is that this is not a sustainable solution. Correct? Okay. If I model this R as a parallel R, then the frequency does not change, even though I have not drawn it well. It looks like the frequency is changing. But I mean, we have seen this in one of the previous, when we were talking about passives, that if the R comes in series with L, then the frequency can change. The R comes in parallel to the LC, frequency doesn't change. But the key thing that to focus here is that eventually it will die off, and if it dies off, nothing can be of any use. Okay, fine. So what is the solution? The solution, in a very mathematical sense, is the fact that if I have an R, right, if I have a lossy element R, which is taking away energy from the tank, then I should have a generative element which probably can push energy in the tank, right? So if R or G, as in the conductance, gives me loss, then if I am able to put another negative of G in parallel to this RLC contraption, then I should be able to negate that loss, right? So that's all that theory is telling us. That is what I'm saying is we have this R here, or let me put a conductance, and let's say I put a negative conductance here, G, negative G, then what is the effective loss? The effective loss is 0, because these two in combination with each other will cancel each other out, right? Now the question is, how do I get this negative of G? So clearly this negative of G does not exist like in R. So we have to generate it, right? And also, I mean, very intuitively speaking, negative of G, if R is taking away power, which means negative of G is pushing in power, which means an active circuitry has to be involved, right? Okay, what type of active circuitry should we be looking at? So let's see, how do I use an active circuit to get a R in the first place. Let's use a simple NMOS device. So let's say I have an NMOS device. Let's say it is grounded source, right? And let's say I keep a test voltage V test here. Okay, if I keep a test voltage V test here, I would like to have a current that is drawn, that is V test over R, correct? Which means that, and I am talking in a small signal sense, which means that if this increases, the current, that is current, if current is V test over R, right? So if the drain voltage increases by delta V test or delta V, the current that will go from drain to source will be V test over R. Now, assuming we are neglecting channel length modulation, this is not possible unless we do something to the gate. So what do we need to do to the gate? So note that what am I aiming? I am aiming for increasing the drain voltage, right? While I increasing the drain voltage, the drain to source current should increase. And if I neglect channel length modulation, the only way I can ensure that this action takes place is if I also increase the gate voltage, right? So if this increases, this should also increase. And this is typically done by, in general, by short circuiting the drain and the gate. This is a diode connected transistor, right? But diode connected transistor gives you a positive resistance, correct? So this is basically, this gives you V test times GM, correct? But I want negative resistance. So what should I do? If I use the same sort of thought process, then what do I end up with? I see that, let's say I have I apply a test voltage source, correct? And what do I need? If this voltage increase by delta V, I want negative resistance, which means that I want the incremental current to be pushed out, correct? I want the incremental current to be pushed out through the transistor, right? So if incremental current has to be pushed out, then what should be the gate voltage? So if the incremental current has to be pushed out, what should be the gate voltage? The gate voltage should go up or go down. So clearly the gate voltage has to go down. If the gate voltage goes up, then the current goes from drain to source. I want the current to go from source to drain, which means this voltage has to go down. So I cannot now, as you can see, I cannot simply now connect this to this, because if I do that, then the current will not get pushed out. So which means I need an inversion, correct? So I need an inversion. Let's say invert by 1 and give it here. Then, so this becomes negative delta V. So this current becomes minus GM times delta V. So your R test, if this is delta V, so your delta V over delta I, if this is delta I becomes minus 1 over GM, correct? So hence you get a negative resistance. Now how do I get this? Negative 1? So now that should be simple to do. There are so many ways of getting a negative voltage gain using common source amplifiers. So what should I do? I basically take, let's say, another common source amplifier and put a R here. So this voltage is how much? So I have a delta V here, or a V test. You can think of it like a delta V or a V test. So this volt, if this current will be Gm times delta V, so this voltage is minus Gm times delta V times R. So all I need to do is to connect this to this, right? So the current that flows up in this case is, this is also Gm, right? So this becomes Gm times Gmr times delta V, correct? So basically the gain of the second stage time delta V going up. So this is delta I. So delta V by delta I, or if I simply say delta I by delta V, which is the effective G, this is equal to how much? Negative of Gm times Gmr, correct? So you get a negative resistance, correct? So now what do I need to do? Now that I have figured out a way of generating the negative resistance, I have to replace that negative resistance in place of this negative G, correct? So what should I do? All I need to do then is, I know that I have this LC circuit, I have this LC tank. I can simply connect, by the way all are incremental till now, I have not shown biases. I can connect them like this. So C is L, and I have obviously I have a resistance, parasitic resistance R, and I have to ensure that the overall resistance looking down from here, right, whatever is the resistance that is looking down from here, that should be equal to negative of G, that is negative of 1 over R, then I am good, right? So what is that resistance that is looking down? So the resistance that is looking down, we kind of did it in this manner. So by the way, I mean, we can as well connect this RLC at a single ended. The part that I missed here is that I could have as well connected this RLC. I could have as well connected the RLC here, correct? That would have also worked. But now given that I have an identical arm on the other side, which is also kind of giving a negative resistance, because whatever is happening to the left side is also happening to the right side, then I may as well use it, right? So which means that I can have this RLC like connected as a floating terminal between the floating nodes of this two transistor configuration, right? By the way, this configuration is often called cross coupled pair. So next thing we should find out is what is the effective negative resistance this cross coupled pair gives us, right? So let's see that. Just like when how do you find out resistance of anything? You apply a test voltage source between the ports that you are interested in and find out the current, right? That's what we are going to do. So here I am interested in between these two terminals. I call this, let's say, V test. I call this I test. I have to find out V test over I test. Okay. So this I test flows through this and flows up through this. So if the I test flows down through this, which means the voltage that has to accrue here is I test over Gm, and the voltage that accrues here is minus I test over Gm. Okay, so which means that this voltage here is I test over Gm, and this voltage here is minus I test over Gm, correct? So what is V test then? V test is effectively equal to minus 2I test over Gm, which means your V test over I test is minus 2 by Gm, right? Or your basically I test over V test is minus Gm over 2, right? So which essentially means that if you put which means that if I decide to put this RLC here, then I have to ensure that 1 over R, that is G, has to be equal to how much? Gm by 2, right? Right? So if we ensure that, then we'll ensure that the entire resistance gets cancelled off and we'll have sustained oscillation, right? So now the question is, how do I give a bias to this? So as you can see that because we have an inductor, it is probably easy to give bias, because what I can do, I can split the inductor between two parts. I can split the inductor between two parts and connect a VDD here, correct? Which means that the DC quiescent voltage here and here are VDD, right? Which means the gate is also a VDD, which means that your transistor is under quiescent condition, they are in saturation, right? So all you have to do is to ensure that the W and the L are such that this condition is met, correct? Now the question is, how do I ensure that this is exactly equal to, I mean, the GMs vary and Rs vary and everything varies. So how do I ensure this is exactly equal, this equality exactly holds? In fact, you'll never be able to ensure that this equality exactly holds. But what do I know? Do I need to exactly match this as a design? As it turns out, no. What we need to at least do is to ensure that your conductance is not less than 1 over R. So effective conductance, which is Gm over 2, should not be less than 1 over R. Correct? If it's less, then you are in trouble, because your oscillations are going to dry off. But what if it's more? What if the negative conductance is more? For that, I'll take you back to this waveform. So you had this R is positive, R is greater than 0, hence the oscillations were dying off. If the R is negative, right? If the R is negative, then what is going to happen? The oscillations are going to expand. It is going to the amplitude are going to go up and it will eventually go to infinity, right? I mean, you can work it out. You can find out the effective impedance of this network with taking R into account. And when R is negative, find out the location of the poles. You are going to see that the location of the poles will go to the right hand side, and eventually everything is going to blow off, correct? But now if I use the same analogy here, so if let's say Gm by 2 is less than 1 over R, then obviously oscillations die off, right? But if Gm over 2 is greater than 1 over R, then what is going to happen? Oscillation amplitude will increase. Okay. So which means it will probably start off with something like this, then it will keep increasing. But can it keep increasing for indefinite time? I mean, obviously it will start off around VDD. Obviously no, because I have a transistor, right? So if it cannot really go beyond, I mean, on the higher side probably you can go, because there is no upper limit, because I have an inductor, it can sustain amplitudes higher than VDD. But on the lower side, at least I know that it will be cut off by the VGS of the transistor, right? So which essentially means that there will be a limit to the oscillation, and whenever you hit that limit, right? Whenever you hit that limit, your oscillation is going to sustain. Now, mathematically, how do I show what is that limit? Mathematically, we will not prove it here, but at least intuitively you should be able to appreciate the fact that this limit, eventually there are two actions at play. If you start off with Gm by 2 is greater than 1 over R, your amplitude will start growing, right? So as the amplitude is starting to grow, effectively what's going to happen, your transistors will start to go more and more into triode for significant amount of the time of the cycle, correct? So effectively I can say that the overall effective GM there will be a compression effect of the overall effective GM. If you think of the way we are because of distortion in LNAs, and when we are talking about distortion and compression of amplitude because of distortion components coming into picture, we saw that eventually the gain compresses, right? The similar effect starts to come into play here. That is, as the amplitude keeps on increasing, the effective GM will start to reduce. A compromise solution will be reached where the effective GM balances this 1 over R, right? So the good thing about an oscillator is you do not physically have to match a design where the negative resistance exactly matches the positive resistance. If that were the case, it would have been trouble, because we cannot, in a semiconductor, you cannot ever match everything effectively, right? There will always be some deviation. But the good thing is that as long as you are more than what you require, right, you know that your oscillation are going to sustain, and there will be a limit to the amplitude, and the amplitude limit will be set by whatever whatever is the distortion characteristics of your transistor, such that the overall average negative resistance should be equal to the average positive resistance, right? You are effectively going to get an oscillation, right? And oscillation frequency will be 1 over under root LC times 1 over 2. Okay. So there is another way of evaluating this condition for oscillation, and that is from a control theory standpoint, and that is as follows. I'm sure you have seen this in your control theory courses. Let's say I have a loop, negative feedback loop, with a forward path gain of G and the feedback path gain of H, right? So what is V naught over Vi? This is G by 1 plus GH. So if GH is equal to minus 1, right, the loop gain is equal to minus 1, we get sustained oscillation. Correct? So what is the loop gain? How do you find out what is loop gain? So to find out loop gain, input is not required. So you break the loop somewhere. Let's say I break the loop here. If I can break the loop, it is not straightforward to break the loop every time. So I apply a V test here, and then this becomes G times V test. This becomes H times G times H times V test. So this becomes minus GH times V test. So the loop gain is basically the return voltage divided by, so your loop gain is return voltage, which is minus of GH times V test divided by the applied voltage, that is V test, right? And negative of that, right? So this is L. So this is GH equal to minus 1. If the loop gain becomes minus 1, then you have, which means this is minus GH. If this becomes minus 1, then you have sustained oscillations, right? Okay. So can we show our LC oscillator with cross couple pair satisfies this condition? Let's see if we can show. We do not have to bother about that LC part, because all we are interested is to see if we can take the loop gain to cancel out if we are getting the sustained oscillation condition under the condition that I have only R and the GM, right? Because the LC parallel combination of LC at resonant frequency is going to give me infinite impedance anyhow, right? Okay, so let's do that. So this is our right. This is our effective configuration, right? So let's break the loop somewhere. Where should I break the loop? So let's break the loop here. So let's say this is still connected. So I break the loop here. Okay. So I apply V test. So before I proceed here, let me go back and correct one of the definitions. So the loop gain is GH, right? So your loop gain is, definition of loop gain is GH. So this is loop gain. This is L. So V return over V test is minus GH is essentially minus GH. So your loop gain is essentially minus V return over V test. So this negative sign is important, otherwise you're going to get all sorts of weird behavior. So let's return to our topology. So we have applied an incremental voltage V test here, and we would like to see the return voltage here, right? Okay. So if we apply a V test here, this current that is going to flow through is Gm times V test. And where will this current flow through? This current will effectively go like this, right? So this current that will going to go up through this transistor is in the upward direction, which essentially means that this voltage will be minus V test, which means this voltage is minus V test, correct? Okay. So the current through this is again Gm times V test, which means the voltage drop across R is how much? The voltage drop is Gm times V test times R, which means this voltage is this minus V test plus that drop, that is Gm times V test times R minus V test, correct? Okay. So but our return voltage is this, basically Gm times V test times R minus V test, which means that my V return over V test is equal to Gm times R minus 1, which means my loop gain, which is negative of V return by V test, is 1 minus GMR, and this has to be equal to minus 1, right? This is for oscillation, which means that my Gm times R has to be equal to 2, which means R is equal to 2 by Gm, right? So this is the same condition that we get back using the loop gain analysis. Now depending upon what type of oscillators that you are planning to analyze, you might want to choose which analysis you would like to go ahead with, right? Both of these analyses that I showed you are equally valid, but each of them are going to give you different types of insights. Okay. So now you might wonder that we have kind of neglected all the second order effects, right? I mean, for example, we have neglected the channel length modulation. What happens if I do not neglect the channel length modulation? So I have the tank here. I'm not sketching the tank now. If I do not neglect the channel length modulation, then I am going to have a GDS here, right? Correct? Or I can simply say I have an R here, RDS, and this I have an effective R here, right? So you kind of see that these two RDS comes in series with R. So instead of trying to compensate for R, you compensate for a different resistance, right? Okay. What about the parasitic capacitance? What impact will that have? So I have a parasitic capacitance here, I have a parasitic capacitance there, right? So this is, let's say, CP. What impact will that have? You can think of this as, if you think, the easier way to think about this is, if I assume, there's nothing to assume, but these two are antisymmetric sides, right? Like just like a differential pair. So we can basically assume that there is a virtual ground somewhere in between, right? Even if you do not assume, you can make an actual ground in between. So see that now this C and this CP are essentially coming in parallel. So your resonant frequency is going to shift, right? So when you are designing, you have to take this into account. And if you are not confident, you need to have a capacitor bank, right? A parallel capacitor bank, in order to shift the resonance frequency back to wherever you want, right? That is quite possible because, in fact, you target certain frequency, and it is quite probable that the frequency at which the LC oscillator comes out is probably not the same, because you estimated the estimation of this parasitic capacitance are wrong. So in that case, you should have an option of having multiple of these extra capacitances to be switched in and switched out using series and parallel switches, and that you can use to restore the center frequency back. Okay. So now this kind of gives us a framework of designing an LC oscillator with negative resistance. But what about electronic programmability? What is electronic programmability of a center frequency? I know that F naught is basically 1 over 2 pi under root LC. It is not very straightforward to change L. While you can do that, there are architectures which changes L, but the easier thing to do is to change capacitance, especially at lower gigahertz frequencies. Now, how do I change capacitor? I can have, just like I said, I can have switched capacitor banks, but that is at a discrete way of tuning. If you want a continuous tuning, how can I go about doing it? So the way to do about doing it is, I would like to remind you of your basic device physics. If I have let's say, a MOSFET and with a source, body, drain and bulb connected together, and I change the VGS or VGB of the MOSFET, and I check the capacitance between the gate and the source, right, in this configuration. If I check the CGS, what should I get? At CGS is equal to 0 or negative, assuming threshold voltage is positive. If CGS is equal to 0, let's say this is a threshold voltage, at much lower than the threshold voltage, what do I have? I have accumulation, correct? So essentially it's a parallel plate capacitor with the metal on one side or polysilicon on one side and majority gadolinium on the other. So I get a maximum capacitance, that is Cox. This is CGS per WL. So I get Cox. As I go closer and closer to inversion, right? As I am going closer and closer to threshold voltage, I encounter depletion. When I encounter depletion, the capacitance reduces. And then when I am around inversion, this is obviously not to scale. So you are going to see something like this, and this is accumulation. This is inversion. Note that I have drain and source exist together simultaneously, right? Okay, so this is not the case in which drain and source does not exist. This is not a MOS cap, right? It has a MOSFET with drain and source together. So now you see that in this region, it seems like if you bias your MOS cap in this region, then there is a chance of getting a voltage variable capacitance, right? In this region, I have a variable capacitor, and the controlling variable is VGS, right? So hence this is called a varactor. It's called a varactor configuration. So how do I change the VGS? So I can, so firstly, I mean, instead of, if I sketch it like this, so all I can do is maybe connect the gate as is and have a control voltage here. Right? So now if I change the control voltage, if I increase the control voltage, let's say the control voltage goes from being, so if the control voltage is 0, it is in inversion, right? So VCTL is 0, which VCTL 0 means VGS is high, which means your CGS plus by WL will be Cox. And as you go closer and closer to threshold, if I go closer and closer to VDD minus V threshold, which means your CGS is going towards threshold, your Cox is going to reduce. Correct? So in this region, you are having a continuous, you have an analog way of controlling the capacitance, right? Which essentially means that if I check the frequency, essentially means that, let's say with respect to time, I I increase my control voltage, right? I'm increasing the control voltage from here to there. So I'm going from, let's say, 0 to VDD minus threshold voltage. What should I see at V naught, where V naught is, let's say, V naught is the difference between these two plus minus terminals, or maybe one of the terminals. What should I see there? I should obviously see for each of these points. For each of these points, I should see a particular frequency. But as I am increasing the control voltage, the capacitance is decreasing, which means the frequency is also increasing, right? Which essentially means that you are going to see an increasing frequency, and so on, right? You are going to see an increasing frequency, right? Okay, that's one way of controlling your frequency. Okay, so there is another way of expressing the same thing. So before we proceed further, I want to mention one thing, that is, if you think about it, what is the relationship between V control and the frequency? It's that of proportionality, right? There is an offset, obviously. It's not like V control equal to 0 corresponds to 0 frequency, but ultimately the relationship between V control and frequency is, so if I say F out is the frequency output, so there is a offset frequency which is often called a free running frequency, right? Plus something which is proportional to V control, right? So I'll just call it K times V control. And what is the relationship between phase and frequency? That is that of integral, right? So essentially you get, if I see phi out is equal to phi free plus integral of K times V control times dt, right? Okay. So this is something that we should keep in mind going forward, right? Because there is an integration operation between V control and the phase at the output, right? So that will be important in the next part of the discussion. We should keep that in mind. So now the question that should arise in our mind is, it looks like we have a way to generate a frequency. It looks like we have a way of varying the frequency based on the requirements that we have. So now, so then we should be done, right? In principle, it should be done, but the problem is, there are a couple of problems. One is, even though it might seem like the LCVCO can give you very accurate frequency, one of the problems is that the drift of the frequency is, with respect to time, is not very good. Which, by that, what I essentially mean is, the values of these components L's and C's, they keep changing very slightly over the course of its lifetime. It is equivalent to saying that, let's say you have an analog clock that is hanging in your room. You hang it, you set it up with, and you match the time with respect to your cell phone clock, and you leave it. After a month or so, you see that there is slight deviation in the time that your analog clock is providing, right? So that is because the internal oscillator that your clock has, its ingredients have slightly changed. The values of L's and C's have slightly changed. Now, analog clocks that you hang in your walls are far more accurate than, are far more stable with respect to the drift of the frequency, drift of the values of the L's and C's, equivalent L's and C's, than the actual L's and C's in an integrated circuit, right? So these actual L's and C's in integrated circuit, they drift, have much higher inaccuracy than the external clock sources that you get, right? So in general, we that's why we all cell phones, or even all receivers, almost all receivers which require accuracy in terms for clocks, will rely on a separate crystal oscillators which have a accuracy of, or drift of, almost a few parts per billion, right? With respect to, with respect to its accuracy, right? I forget about the parts per billion and all, but the key thing to note here is that uh, the quartz crystal that you get separately, which is just like a SAW filter which cannot be integrated on chip, a quartz crystal cannot also be integrated on chip, but it is extremely accurate with respect to that anything that you get on the chip, right? But the issue with, just like you have a quartz SAW filter which is non-programmable, most quartz crystals are also not programmable, in the sense that the frequency output that you get from a quartz crystal is constant, more or less, and you do not really get very high frequency output from a quartz crystal. It is commonplace to get few megahertz, tens of megahertz, hundreds of megahertz, but anything beyond that, it becomes expensive and it's not so suitable to get. And that is why what we need to do is to, if we want to use a quartz crystal, so we want to use, so first problem is LC's drift with time. So this is not a good thing. So we need to lock the frequency to a stable reference, and which is generally a quartz crystal. Correct? So assume that you have a quartz crystal which gives a very almost near ideal clock source. Correct? And I want to generate an output which is not necessarily this frequency but multiples of this frequency. Let's say this is 100 megahertz. I want to generate a 1 gigahertz frequency which has similar amount of accuracy. So what should we do? So that's the next part of discussion. So before going there, let me go to a negative feedback loop that we are familiar with, that is that of a voltage negative feedback loop. So let's assume that I have a voltage of V naught. I want to get a voltage of K times V naught using negative feedback. What do? I basically generate a negative feedback loop where I first divide this voltage by K, right? Sorry, this is Vi. I want V naught to be K times Vi, right? I want V naught to be equal to K times Vi. We want. So I divide this voltage by K, so this becomes V naught by K. I compare it with Vi. Comparing is basically a subtracting operation, so this becomes Vi minus V naught over K. Then I integrate it, amplify it or integrate it, right? Integrate over time, and then use the integrator to drive the final output, right? The integrator at a very low frequency, integrator has a very large loop gain, right? So if at very low frequency, assuming this is a low frequency negative feedback loop, and at the frequency of interest you have infinite or very large gain, then this V error, that is Vi minus V naught over K, so VE will tend to 0, which means that, so if loop gain is tending to infinity, then VE tends to 0, then Vi minus V naught over K tends to 0, which means V naught tends to K times Vi. Correct? So this is the mantra with which negative feedback loops in the voltage domain work. So here we want to use the same mantra to drive to multiply the frequency, right? Not the voltage but the frequency, right? So what do I need? So I have an input which has a certain frequency. We are not talking about voltage, by the way. This is Fin. Fin is basically the number of times I have rising edges per unit time, right? So that's essentially Fin. And I want F naught, which is, let's say, n times Fin. So just like that, what do I need to do? I need to first take and divide the frequency, not the voltage, right? I need to divide the frequency by n. Correct? So how do I divide the frequency? If this is a square wave going from 0 to 1, how do I divide the frequency? I can use a divide by n counter, right? This can be a divided by n digital counter using flip-flops, right? Not very difficult to do if the frequency is not going up to like tens of gigahertz. Not very difficult to do. So all digital circuit, right? Fine. So here I get f naught by n. So what do I need to do next? If I go back here, I need to generate this error voltage in some error signal, which I want to then amplify, all right, or integrate. So here this is entirely voltage domain loop. We are trying to increase the voltage by a factor of n. So we are generating a voltage error. Here this is a frequency domain loop. I want to multiply the frequency, so I have to generate a frequency error, right? I have to generate something. I have to put something here. So that the output is the difference of f in minus f naught by n. So now can you think of a block that generates a difference of frequency? We have been doing this from almost the beginning of the course. It's a mixer, right? So it's a mixer. So I put a mixer. It will generate both positive and negative frequencies, but I want only the negative frequency. Then what do? I put a low pass filter. To filter out the higher band, correct? Okay, so I put a low pass filter, and then what? So where are we now? We have this VE, correct? And then what do? We have to integrate it, right? Or before I move forward, the stuff that we need to be aware of is the fact that the variable of interest here is frequency. Variable of interest here is also frequency. What is the variable of interest here? What do I get? When I say that I'm getting a waveform of f in minus f naught minus by n, here it is a slowly varying waveform, right? So I would say this is if the loop is perfectly operating, then f naught is equal to nf in, then this difference is 0, right? So this here is a very slowly varying voltage waveform. Correct? So now what will be the purpose of this voltage waveform? The purpose of this voltage waveform, what information does it have? It has the error information. It is the error information that would help us in driving the output towards the frequency of interest, right? So if this voltage is increasing, right? So let's say if this voltage, so for some reason I found that this voltage is increasing, correct? I can associate this increasing voltage to assume that the loop wants the output frequency to go up, right? And what should I put here so that the output frequency goes up? I can put our voltage control oscillator. VCO. By the way, I have not shown you the symbol of this VCO. So this symbol of this VCO is this, where this is V control and this is V out, right? V out as in this case, I should ideally say F out. Okay. So I put a voltage control oscillator, and if this voltage goes up, this will try to push the voltage push F naught to higher and higher frequency. And under what condition will it stop? It will stop, at least in the block diagrammatic sense, it will stop only when this guy reaches, this becomes Fn, right? The loop stops only when this also becomes Fn, because when this becomes Fn, the error voltage becomes DC. If error voltage becomes DC, this voltage stop ramping up or ramping down, which means your VCO stops. The V control stops, right? V control does not go up or go down. V control only stops to a steady voltage, right? So VCO control voltage or V control. Let me just call this V control. V control stops ramping up or down only when or F out becomes NF in, i.e. F in minus F naught by N is equal to 0. Right? So hence your frequency gets locked to N times M times F in. So this is called a frequency lock loop. This is called a frequency lock loop or FLL. Okay. So by the way, if you simply do this, it is likely that it is not going to work because I made a convenient statement that it goes up and down. But in a negative feedback loop, monotonicity is important. You cannot really say that if I change V control, it goes up, or if it goes change V control, it goes down, and I put the negative feedback loop regardless of the sign, is going to work. No, it's not going to work. So you have to. That's why whenever you have a circuit like this, topology like this, there has to be an auxiliary circuit which starts up the circuit in such a way that it goes in a monotonic direction, and then the system starts to lock, right? So that is something that you should keep in mind. So this is what we call an FLL or a frequency lock loop. Now there is another version of this that is called a PLL, which is a phase lock loop. And what does a phase lock loop do? Just like in a frequency lock loop, you are locking the frequency. In a phase lock loop, you lock the phase, right? So here there is no constraint between what will be the phase of F in and what will be the phase of F naught by N. Which what I mean is that your F naught by N can be like this. F naught by N can be like this. It does not really matter. FLL will honor both kind of output. But in many applications, you would want phase to be exactly known. For example, an IQ receiver, you want a specific, you would like to have a specific knowledge of the phase. You do not want the phase to move around, correct? So which means that you would like to lock the phase also. So now what is the difference between a frequency and a phase? You need one integration, right? So essentially in a block diagrammatic sense, all you need is, let's say you have a low pass filter and you put another set of integrator, and then you put a VCO, so this becomes your PLL, right? So here this is your F in, your F naught by N will also get locked, correct? So this is a phase lock loop. But the issue here is if you think about it in the phase domain, in a phase domain, this is an integral, right? It's a voltage control oscillator is an integral in a phase domain. If you recall, this is what we saw. Where did we see? This is the integration in a phase domain, and I am putting another set of integration. So effectively I have a double integral. Now what happens if you have a double integral in a negative feedback loop? You can get instability, right? So essentially, so what happens if you have a double integral in a negative feedback loop? You get instability. So you need a additional 0, right? So this will cause double integral causes instability, which means that we need a 0 in the transfer function, 0 in the loop. So I will not go into how to design the PLL with the 0 in the loop, but the thing that you need, when you look up PLL, you should always keep this in mind, that a PLL will not work if you just put your block diagram in this format. The final thing that I would like to also mention is that this is not the most popular configuration of PLL. The typical PLL configuration requires a phase and frequency detector. So these things are combined into something called a phase and frequency detector, or it's called a PFD, correct? So, and there are different ways of generating. There are different ways of designing the PFD, right? Um, so I would encourage you to look into textbooks, and if possible, you can also sign up for the NPTEL course on PLLs, where these things are covered in much more detail, right? So with this, let me do a 2-minute recap of what we did. Starting from the very beginning, we wanted to design. We wanted to have an idea of how an RF receiver or a transceiver looks like. We spent considerable amount of time dealing with the receiver. So we starting from antenna, we have a transmission line, we have a SAW filter, right? Then the thing goes inside the chip. We have an LNA. Then we have a mixer. We have IQ mixer and so on. And then you have a low pass filter, and after the low pass filter, you put an ADC and all. We obviously did not talk about the ADC. To a large extent, we have covered each of these blocks. Hopefully that this course serve as a stepping stone for you to take up designs of any of these blocks with more of a knowledge than whatever you had, and more of a knowledge and more intuition than whatever you had while coming into the course. As you might have noticed that if you go through a textbook, any of the reference textbooks that are listed in the course website, there are lot many other architectures that one can go through, right? In RF while designing RF systems, and physically speaking, there is not possible. It's not no course can cover all the architectures that one might encounter, right? And architectures, different types of architectures are still getting evolved. So my motivation of offering this course to you was the fact that if you understand the basics or the root or the underlying assumptions and the underlying design principles and the guidelines that have helped designers in the past to think about these problems right from scratch, right? So you should be able to take up those principles and run with it, right? It's not as if I give you a circuit and ask you to analyze, and you sit and write KVL and KCL and run simulations. You should be able to critically think about why the circuit came into being in the first place, right? So once you start thinking from that perspective as to why the circuit has come into being in the first place, you should be able to appreciate a designer's mindset. And inculcating a designer's mindset was essentially the aim of this course with regards to RFIC design, right? I hope you have enjoyed the course, and I have learned a lot, and hopefully you have learned a lot along with me as well. Thank you.